So before I start talking about magnetic fields and the force and how it's generated, I quite want to first focus on the Lorentz force and how we can see how that relates the magnetic field to the electric field. Because at the moment they seem quite different. They're both forces, but they act in different directions. This has a cross product, and you have to be moving in order to have a magnetic field, for example, and to experience the magnetic field. So it gets quite abstract to relate these two. But the reason we're doing them together is because they actually have been unified. And there's a way of understanding how they are unified. You can go very much in depth and go in and use special relativity and some more complicated math to do it. But I just want to give a quick overview and just at least a bit of a feel. So the first thing I'm going to do is I'm going to define the electric and the magnetic field, but I'm going to use this constant K, K defined here, and then I'm going to relate the two, the use of the one used in the magnetic field versus the one used in the electric field is related by this factor of c squared, where c squared is the speed of light, which is also the speed of light squared, which is also 1 over mu naught epsilon naught. So that's the magnetic and electric constants respectively. And then we can see that if we have k over c squared, we're just going to have this term, which is usually what you have here for the magnetic field. And this already gives us a hint that relating these two is going to have something to do with the speed of light and therefore special relativity that we're going to cover later. One of the things you can immediately notice is if you take one of these c's and you put it under this v, you're going to get a term that we're going to see often in when doing special relativity, and that's the beta term. And the beta term, we can just define that as v over c. And this is quite an important term since it relates basically your speed versus the speed of light. So the beta is always the size of beta, your absolute value of beta is always less than or equal to 1 because you can't go faster than the speed of light basically. And then we can also do some manipulation, so we get a c here and then just a v over c here and then a k and a k. Well, not a k, some other constant. But and that gives us a hint because what we'll see later on, I'm not sure if we're going to cover this year, but the electric field is related to the magnetic field in a very specific way, in that for the magnetic field you have to be moving through space in order to generate it and in order to feel it. But the electric field is generated when a charge is moving through time, and it's felt when a charge is moving through time basically. And we'll see that our electric field is going to get a little gamma term in here to account for time dilation. So if your time is going slower because you're going faster, which we'll cover in special relativity, then your electric field that's felt and generated is going to be less, but the magnetic field that you will feel and generate will be more. And that's in the end they cancel out such that the Lorentz force is constant in any frame of reference, so no matter what speed you're going. Because at the moment, if we just look at this isn't quite the same. If I'm going a certain speed, then I'm going to feel the magnetic force, but then when I'm not moving, I'm only feeling the electric force. So if I'm in a different frame and I just go, for example, in a car driving, then I suddenly have a velocity. Now I have to feel the magnetic force, but the person that's standing still next to me won't. And if I drive next to that car, for example, then I see that the car isn't moving, so he shouldn't feel an electric force. But if I'm standing still and looking at the car, then he is moving and he should feel the magnetic force. You see, so it gives contradictions like that if you don't relate the two to each other. You'll also see that if you do the calculations, there's a curious thing where Newton's third law isn't directly respected by this force. So the force from one particle on another due to the magnetic force is in a different direction than otherwise. So they don't exactly cancel out. And that's because of the interaction with the fields. So the electric and the magnetic field themselves actually have energy and momentum. So you have to account for that in order for it to make sense. So there are a lot of strange things that gets introduced in electromagnetism. And it's also one of the reasons why, it's the main reason actually why Einstein had to develop his theories, was because it didn't make sense without it. So it's a very important thing, and its unification between the electric force and the magnetic force by Maxwell was a very important thing for physics. So I think understanding that they are related and just having a feel for in which way that is a very important thing before even starting working on the magnetic field, which can sometimes be quite weird.